Welcome to the another session in Frontiers in CFD. Today we have CFD simulation of 18 cell lithium-ion battery pack with air and water as a working fluid. So preferably first thing we are going to do is with air as a working fluid. Today's objective is to prepare the geometry of lithium-ion battery cell which is suitable for liquid and air cooling, to generate the mesh on computational domain and visualize the element size and the name selection, to run the setup and visualize the result for liquid and air. So preferably we'll be using liquid as water and air will be used as a working fluid. So these are the geometries which we are going to follow. For this particular case, height will be 65 mm. So along the cells are along with the casing. So this is the simulation that at the end of the we can say performing the iterations, you will visualize such kind of simulation. So how the temperature variations are there taking place, so that we will visualize with the help of we can say one of the video which you can see here. So how the temperature variations are taking place along the cell, how the heat has been carried away by the fluid, so how the variations are temperature taking place at the front, as well as how much will be the temperature at the end. So this is all will the simulation will do right from preparing the geometry to visualizing the result. So this will be the step-by-step process for this. So this is one of the sample video for this simulation which has been generated. Welcome to the another session. Today we will see the CFD simulation of 18 cell lithium-ion battery pack. First of all, we will prepare the geometry, and once the geometry has been prepared, we will do the analysis for the same. We'll generate a different graphs with the help of the given heat generation per unit volume. So the dimension that we are going to follow are these are specified. So this is along with the casing has been provided. The cells are there of 18 mm diameter and 19 mm is your casing, and we have this whole dimension for your battery pack. So first of all, we'll test this with the help of air as a working fluid, and second thing we'll test this as a water as a working fluid. So first of all, let's start with the fluid flow fluent option. Here in geometry, I will click new design modular geometry. So with the help of new design modular geometry, just create a XY plane first, set up the units to millimeter. So create a primitive that is a box. So as per the shape of we can say this is 200 by 150, sorry 225 by 150. So X component will take it 200 255, and Z component will take it 150 here, and the Y component will take it 65, and accordingly we will proceed. So let's make it add to frozen and then make it generate. So we have generated a kind of pack. Now in that we will go on to add some cells. So create, go to the primitive that is cylinder. Instead of add metal, make it add slice metal. X coordinate I will keep it as now just check the first object what dimension we have to follow. So this is the first cell is at a distance of 25. This is 35 from the top, and the 25 in the horizontal direction. So X will take it 25 here. X component will take it 25. Z component I will take it 35. So it will be somewhere here. The radius will be taken as 9. This Y component will be 65, and the remaining component I will make it 0. So 18 mm diameter cell we are considering. So make it generate first. So create one more time, that is primitive, that is cylinder. Instead of add metal, make it slice metal. Now x component will be as per the dimension we have 60. X component will be 60, z component will be 35, that will be as it is. Just check one more time. Yeah, 35 as it is. This will be 65. Next component will be equal to 0, and let's make it generate. So second cell has been generated. So create primitive, that is cylinder. Instead of add metal, I will make it slice metal. X component now will be here. The next is 95. So put it 95 here. Then z component will be 35 as it is. This will be 65. This will make it to be equal to 0, and let's make it generate. So we have generated 3. So let's go to create one more time. Let's make it primitive, that is cylinder. Instead of add metal, make it slice metal. So now it will be 130. So x component I will take it 130. Z component will be 35. This is as it is. This will be 65. This will make is equal to 0, and let's make it generate. So fourth cell has been generated. So primitive, that is cylinder. Instead of add metal, I will make it slice metal. X component now will be equal to 165. So x component 165. This will be equal to 35. This will make it 65, and the remaining component will be equal to 0. So let's make it generate. So the 5 are been done. So last one, create primitive, that is cylinder. Instead of add metal, make it slice metal. So this is 200 now. This will be 35 as it is, the previous one. Make it 65, and let's make it 0. So let's make it generate. So the one for one row we have done. So similarly we have to do it for the second. So for second again, the distance will be 75. So create primitive, that is cylinder. So instead of add metal, make it slice metal. X component will be now first 25, and z component will be equal to 75. So we will be at second location. Make it 65. Let's make it 0 here. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component first was 25, now it is 60. So here 60. Z component will be 75 as it is. This will be 65. This will be equal to 0, and let's make it generate. So this is second one has been done. So create primitive, that is cylinder. Instead of add metal, make it slice metal. Again follow the dimension. So third is 95. So put it 95 here. So this will be 75 as it is. This is 65, and let's make it equal to 0. So let's generate. So create one more time. Go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be now 130. So let's put it 130. Then this will be 75. This will be 65, and let's make this component to be equal to 0. Let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 165. So here put it 165. Z component to be equal to 75. Then this is 65, and the last component to be equal to 0. So let's make it generate. So create one more time primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 200, and this Z component will be equal to 75, and this one will be 65, and the next one will be equal to 0. So let's make it generate. So we have generated the 2. So last one is left. So distance is 115. So accordingly we will do for the last one. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be now equal to 25. Z component will be 115. So this will be equal to 65. Remaining will be equal to 0. So let's make it generate. So next, create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 60. So this is 60, and this Z component will be equal to 115. So make it 115. This Y component will be equal to 65. Z component will be equal to 0, and let's make it generate. So create primitive, cylinder. Instead of add metal, make it slice metal. X component will be now 95. So this is 95. This is now 115, this is 65 here. Let's make this component to be equal to 0. So let's make it generate. So create one more time, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 130. So X component is 130, Z component is 115, this Y component will be 65. This is to be equal to 0, and let's make it generate. So this is slice. Okay, create, go to the primitive cylinder. Instead of add metal, make it slice metal. X component now will be equal to 165, this will be 165. Z component now will be equal to 115 as per the previous one. So this is 65 and this will be equal to 0. So let's make it generate. So one more time, create primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be 200, Z component will be 115, this Y component will be 65, and the last one will be equal to 0. So let's make it generate. So we have generated total 18 of cells, and now it's time to prepare the casing for the same. So create one more time, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 25 here. The Z component will be equal to 35, but the radius now will be 9.5 here. This Y component will be equal to 65 and this will be equal to 0. Now this will form a casing surrounding. So this is how the casing which has been provided on the cell. So accordingly we have to prepare the casing for each and every layer. So let's go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be now equal to 60, Z component will be same, that is 35, this is 65, then this is equal to 0, and let's make it for the second. Let's make it generate. Okay, third is 95. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component is 95, Z component will be 35 as it is, this Y component will be 65, and this will be equal to 0, and let's make it generate. Next, go to the create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 130, so this is your 130. This sorry, X component is 130, this is 35 as it is, this will be equal to 0, and this will be your 65, and this will be equal to 0, and let's make it generate. So create one more time primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be now 165, so make it 165 here. So this will be your 35, this will be your 65, and let's make this equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component is 200, and Z component will be 35, this Y component will be 65, and this Z component will be equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be equal to here X component will be 25, Z component will be equal to 75, and then this is equal to 65. Let's make this equal to 0 and generate. So one by one we are going to generate the casing. So cylinder, instead of add metal, make it slice metal. So X component now will be equal to 60, here X component is 60, this will be equal to 75, this Y component will be 65, Z component will be equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be now 95, so this is 95, this is your 75, sorry, this will be 65, and let's make this equal to 0. So now the casing is done for the third. So create, make it primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 130, so put this is 130, so this is equal to 75, so this will be 65. Let's make this to be equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be taken as 165 here. Y component will be 75. So this one will be 65. Let's make this equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component is 200. This Z component is 75. Y component will be 65, and this will be equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be 25 again. Z component will be 115. This one will be 65. This one will be equal to 0. So let's make it generate. Next, create, go to the primitive in cylinder. Instead of add metal, make it slice metal. X component will be 60 here. Z component will be 115. This Y component is 65. Z component will be equal to 0. So let's make it generate. So create one more time, make it primitive, that is cylinder. Instead of add metal, make it slice metal. So we are moving for the third one. Let's make it 95. This is 115. This will be your 65. Let make the Z component to be equal to 0, and let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component now will be equal to 130, and Z component will be equal to 115. This Y component will be 65. This Z component will be equal to 0. So let's make it generate. So create, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be now equal to 165. Then Z component will be equal to 75. Sorry, not 75, 115. 115. This is 65, and last one will be equal to 0. So let's make it generate. So the last one left, that is a cylinder. One more time, and instead of add metal, make it slice metal. X component will be equal to this is 200. Z component will be equal to 115. Then this will be equal to 65, and this will be equal to 0. So last casing is now generated. So total there are 36 cylinders. You can just check it out. This will be your inlet, and the other will be your outlet. So accordingly we are going to follow. So yeah, so this is one of the casing which one of the case which we are considering. Okay, so first one is your, okay, so one by one we'll differentiate all these terms. So this is your okay, first of all I will select all cells, create, control, and select all cells only. So I will make it form new part here. So I will define this as, say, cell. Okay, so cell has been done. Now I will hide the cell. Okay, and this is your pack. So hide the body. Now I will select all, and I will make it form new part. So this is your casing. Okay, so this is casing and this is your pack. So I will define this here as pack. Okay, so this is pack, then casing. So pack I will make it as fluid, make it okay. Cell, so this is cell 1 2 3 4 5 6 7 8 and so on. So each and everything we need to define here. So this is control V. So we have to do it for all. So to avoid the difficulty in boundary conditions while applying in the setup, we are just giving the name here so that there will not be any error later on. here, so control V, then here is control V, then here also control V, then here also control V. So the cells are defined. Now we will define the casing. So one by one, say casing. Same way we are doing, we are keeping it solid. So we are done, almost done it for all. Okay, so we have defined casing also. Now let's make it show all bodies. So we have casing, then we have pack, as well as the pack is fluid. This is pack is fluid, then cell is your solid, and the casing is also solid. So this is the first part which has been generated. So let's save the work. Okay, so we'll define this with the name. So 18 cell with casing and air water as working fluid. So copy address as a text. We'll define this with the help of the same name. Okay, so we have saved the work so that we can access the works later on also. So the first part which is related to geometry preparation has been done. I will just close the geometry part now and we'll move to the next part. So the next part is your mesh. So click on edit. We will try to have a mesh which is within the limits of I can say the computational capabilities and other limits which we are having. So we will take into consideration that, and accordingly we will generate the mesh. So first of all we will generate a default mesh, and accordingly we will check out how the meshing is been available with us. Okay, so generate mesh. First of all, the default mesh we are generating. If it is required, we'll make it further fine. Right now the number of nodes and elements are 88,026. So this looks to be very coarse. I will put it 0.001 and let's make it generate. So again, that will take into consideration the capabilities with our end, because we don't want the simulation time to be also more. So accordingly we'll proceed. So 60% has been completed. Okay, so 31 lakh 14,000 294. So this is looks to be very fine for us. So but we'll proceed with this. Okay, so let's define few things. This one will specify inlet. This one I will make it inlet. So this one is inlet. Okay, same way we'll to specify this is outlet. Okay, so we have defined two things, inlet and outlet. So I will go to geometry again and I will go to the casing, and I will show hide all other bodies. So I will select the faces of the casing, all faces of the casing. So here I will mention casing convection. Okay, so I define 3 inlet. This is okay, so let's make it show all bodies first. This is inlet, this is outlet, and the casing convection is this one. So now we are okay with this. We'll make it update so that the mesh translation to the Fluent will be successful. So once this message appears here, so here you can see the mesh translation to Fluent is successful. So one more time, just click on save the work. So the first 2 things are been done. Now you can proceed further for the next things, that is for the setup. Okay, so next we'll move to the next part, that is for setup. So by that time we'll close the mesh window because it is not required for us. So close the meshing. Next go to the setup, click on edit. So let's provide the number of processes that computer can run. Make it okay. So we'll try with air as a working fluid, and we'll try with the water as a working fluid for the same. So first of all, define the transient model. So depending on the count you have, so accordingly it will take time, the mesh count which you are having. So select the transient model, specify the gravity. I will put it minus 9.81 here. Then go to the model, energy equation will make it on here. Go with the viscous K epsilon, enhance wall treatment, thermal effect and curvature correction. Then solidification melting is not there, so I am not going to use this. So material will select. So create first of all the Fluent database will take the 2. I will add water also right now, so that we don't have to change many boundary conditions later on. So water, liquid and air are been there. So here, so aluminum will be there as it is. First of all I will specify lithium cell. Here also I will specify lithium cell. Properties of lithium cell I will specify 2775. Then thermal conductivity I will specify 3, and this is 888, so 880 specific heat. So we are done this. So lithium cell we are specifying first. Now I will add aluminum because we want the casing also. So let's go to the aluminum. So make it copy and close. So we have 4 things: water, air, aluminum and lithium. So depending on whichever the case we are running, accordingly we will make the changes. So pack here. Now the first case we are running it with air, so I will keep this as it is. If you are running with water, I will just go with water liquid. So this slight changes you have to make. So let's close this. Casing, the casing should be made up of aluminum. So make it aluminum, make it apply and then close. Okay, so just a minute. Okay, so now it's time to define the cell. I will make it lithium ion. So make it source term here. First of all I will make it 1. So constant heat generation per unit volume. So I will go with some rate around 2C, that is 47579. I will go with the 2C rate first, 47579. Make it apply and then close. So this is what we are done. Now next is boundary conditions. So inlet, I will put some velocity here. So let's say it is 0.5, 0.25 meter per second. Make it apply and then close. Then wall cell is there. So we are just ensuring that the wall cell is lithium. Wall casing also we need to ensure this is aluminum. So that selection you have to make. Okay. So in casing convection you will observe one region over here. So on that casing convection I will specify the convection. So create edit, go to the edit. So I will put casing convection, let's say 5 watt per meter Kelvin. So make it aluminum, apply and then close. So we have to do it for all wherever you are observing casing convection. So there I will put this value. So make it convection, put the value of convective heat transfer coefficient, ensure that this is aluminum. So make it apply, then close, make it apply, then close. Casing convection, here also we have to do the same. So initially we have considered air as a working fluid. So convective heat transfer coefficient, aluminum, make it apply, then close, make it apply, then close. So wherever we are finding casing convection, so there we are going to specify this value. So convection, I will put it 5, make aluminum, make it apply, then close, make it apply, then close. So casing convection, make it edit, convection, so heat transfer coefficient, so make it aluminum, make it apply, then close, make it apply, then close. So we'll do it for all. So just check it here. So make it edit, ensure that the casing convection is verified. So close. So all the things we have to do it. Make it edit. So convection, make it 5. Ensure that this is made as aluminum. Make it apply, then close. Make it apply, then close. So wherever the casing convection you are observing, you have to all places you have to do the same thing. So convection transfer coefficient is 5. And so aluminum, make it apply. So if you are specifying the casing convection, if you are specifying, then only you have to do this. Otherwise, if it is not done, you just have to change the material to aluminum. So make it apply here, edit, edit. So convection, make it 5. So here make it aluminum, make it apply, close, make it apply, close, edit, make it convection, say it is 5, aluminum, make it apply, close, make it apply, close, casing convection, convection, let's put it 5. Instead of lithium cell, I will make it aluminum, make it apply, then close, casing convection, this is edit, convection, make it 5, change this to aluminum, close, make it apply, close, casing convection one more time, click on edit. So convection, make it 5, aluminum, make it apply, then close, make it apply, then close one more time. Casing convection, put convection, let's value the 5. Aluminum, make it apply, close, make it apply, close. Casing convection, make it edit, convection, make it 5. Instead of lithium I will put it aluminum, make it apply, then close, apply, close. Casing convection, convection, this is 5. Aluminum, make it apply, and then close, make it apply, close. Casing convection, edit, convection, so put it 5. Aluminum, make it apply, close, make it apply, close. Convection, this is 5. Aluminum, make it apply, close. So we are done it for all. Now we'll go to the next part. So reference values, no need to do anything. Okay, boundary condition, we just check with wall casing, so make it 5 here, ensure this is aluminum. Okay, now go to the report definition. So new, I will make it surface report area weighted average. So I require temperature. So first of all I will say total temperature. I will define it for outlet first here. So print to console, total temperature at outlet. So I just define the outlet, make it okay. Next is surface report area weighted average. Now again temperature, this is total temperature. I will select now whole system, total temperature, I will make it system report definition, make it okay. So these are the two things we have done. Now make it close. So go to the initialization, click on initialize. While doing this, so first check pack is in fluid, casing and cell in solid state. So this is one thing that you have to ensure. Go to calculation activities, then auto save, let us say 20. Go to the solution animation, new object, let us say contours, put it temperature, I will put it total temperature now. This is for whole system, I will put first, make it float, make it apply, then close, make it close, so save display. Once this is done, then click on close. Okay, so now this is close, select this contour one, I will make it total temperature system animation. Okay, so make it okay, then solution animation one more time. I will select new object contours, total temperature. Now I will select only wall cell here. Make it float, make it save display. So this is now only the portion which is visible as a cell wall. So we need to select the walls of the cell also. So let's go one by one below. So this is contact region TRG, we will select it first. Okay, similarly this is also contact region TRG, I am going to select. So whatever TRG I am going to say, I will select that. This TRG, this casing, this is TRG, 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 TRG. apart from casing and pack which is available, so that I'm going to select here. So let's see. Yeah, almost all has been there. Okay, so make it save display. Then this is close. Make it apply. Then close. So contour 2 I will define as total temperature of cell. Say animation. So make it okay. So cell temperature animation we have set, then total temperature animation we have set. Then we have set the outlet temperature, and in report definition total temperature of system we have specified. So if you want you can specify the temperature of cell also, but there are n number of cells, so each and them will be subjected to the fluid, like the first and last they are subjected to different temperature of fluid, so that's why we are not generating the temperature of cell also as a curve, but it can also be generated. So go to the run calculation. So first of all let's put some value, let us say 100. So again one more time I'm just go with the boundary conditions. So what inlet velocity you have specified? Inlet velocity we have specified 0.25, and with this 0.25 we are going ahead. So just click on run calculate and just click on calculate. So this might take some time. So once the first 20 are completed, you will see the contours of temperature along with the two curves. One will corresponds to temperature curve at outlet, then temperature curve for the whole system, and then you will see the animations related to the cell temperature also. So right now we are able to see the contours of total temperature. We are right now using air as a working fluid. If you are going with the water as a working fluid, so accordingly the things will going to change for us. So we'll wait for the simulation to go further. So by that time we'll just show you this cell temperature which is here. This is the total temperature of the system, and this is the curve. So we have performed around 842 time steps as well as follow time. So this is the situation right now. Contours of total temperature for the system is visible like this, and then contours of this is total temperature for the system. Then contours of total temperature for cell we will visualize. Then this is for your total temperature of system curve and the outlet temperature curve. So this is all done with the help of air as a working fluid. So we are around 844 time steps, 845 time steps, and at 45 as a flow time. So this is done with the water as a working air as a working fluid. So similar things we'll try with the help of water as a working fluid, and we'll check how the things proceed. So we have completed around 1184 time steps as well as the flow time. You can see the temperatures variations over here. So this is the contours of total temperature system which we are using right now as a air as a working fluid. So this is the total temperature system. This is the curve. So this curve will become flat after some time. So that will be the situation where no further changes or the temperature will not go beyond that particular point. So this is the total temperature at the, just a minute, total temperature at the outlet, the for air fluid. So this is how the variations which we are observing right now. We might have to run this for further in order to visualize it in quite better way. But right now we are able to see the comparatively lower temperature here, and same way this is how it can be visualized. So we'll run this further in order to check it when this temperature curve become flat, because there will be a point where after which the system temperature will not go beyond a particular limit. So we are expecting this to become flat. So we'll wait for the iterations to complete and accordingly we'll. So we have run the simulation for around more than 3000 flow time as well as the time steps. You can visualize at the bottom how many iterations are being performed. At the same time, you can see here 325, 3253. That is the number of time steps as well as the flow time which we are run. The cell temperature here is very low as compared to the one which is on this side. So total temperature of the system, you can see here the temperatures are low, and you may see significantly the temperature is increased, or we say higher value on the other side. So if you see the total temperature curve system, so this curve now tend to become flat. So over the period of time, this is likely to become flat, and we may say that the system temperature will not go beyond that particular value. So right now it is 313 over here. So the variations will be are slightly less because it's trying to become a flat curve. Temperature at outlet, it is around 304 Kelvin, and the scale residual you can see, and the total temperature of the system which is for your cell. So this is how the variations in the temperature that can be visualized. We might need to run this simulation for some more flow time in order to understand, in order to see where the curve become flat. So there will be some point, there will be some time steps after which the curve will become totally flat, and that is the point where we can say the system temperature will not go beyond a particular limit. So for a while we'll run this simulation for few more time steps so that the curve will become completely flat, and that will be the end point for us. Thank you. So we have performed around 3909 in time steps. You can see the same flow time. For this, we have the total temperature of the cell. The maximum temperature it shows around 322. You can see some variations because of the fluid flowing. This is related to the contours of total temperature for cell. Apart from that, we have this contours of total temperature for the system that we have seen just previously. Then we have the total temperature system curve. So here you can see 3920 as the flow time as well as the time step, because the number of time steps, the time step size we have taken as 1. So the curve is still Okay, so the curve you can see, it is on the verge of becoming flat, but still it is not there completely flat. So you might need to run the system for some longer duration of time. We already run it for 3920, but it might need to run it further. You can see the variations are very less, that is 313.72, and on the other side is 313.77. So variations are less, so after some time this will become a completely flat, and that time this is the total temperature at the outlet. So scale residual, and this is your total temperature system. So we'll wait till this calculations are completed, and accordingly. So this is the temperature contour for the system. Individual temperature cells that is observed. How the temperature of the system varies with respect to the flow time. You can see the curve becoming flat over the period of time, that is around after 4000 time step, as well as the 4000 as a time value, and the temperature which is slightly lower than 314 Kelvin. So what we can conclude out of is the total system temperature will not go beyond 314 Kelvin. So this is the temperature at the outlet. So what will be the temperature of fluid at the outlet, which is moving from inlet to outlet? So this is the one of the graph which has been obtained here.